Hello, everyone. So thank you, organizers, for organizing this very nicely. So today I'm going to talk about bags of gold paradox. Uh, I'll not go too much into technical details, but we'll try to give an overall picture of this, and hopefully it's self-contained. Okay, so we will start with black hole. So black hole is a space-time S containing a region I where gravity is so strong that massless signals from I cannot escape to its complementary region S minus I. So this region I is denoted as the interior, and its boundary di is called the horizon. Now, black holes also follow these laws of thermodynamics. In particular, we'll look at the second law. Sorry. In particular, we'll look at the second law. So the entropy of the black hole is given by area by 4g Newton, where A is the area of the horizon. And the entropy indicates the existence of a microscopic description in terms of black hole microstates. And any good quantum description of gravity should reproduce this entropy subject to small corrections, since this is a thermodynamical statement. Now, in the black hole spacetime, there exist nice Cauchy slicings. So by nice Cauchy slicings, I mean slices that are space-like everywhere and stay away from the singularity, whose interior volume is very large. And associated with large interior volumes, the semi-classical entropy of this system can potentially exceed this Bekenstein-Hawking entropy, which we just showed. And this leads to a paradox. And the goal of the talk is to understand how such a discrepancy is taken into account. So consider the eternal black hole in ADS, which has two different exterior regions, but a shared interior wormhole region. And this spacetime is dual to entangled but not non-interacting conformal field theories, each of which live on a particular boundary. So this is the Penrose diagram of the spacetime. Here, the vertical lines indicate that the boundaries are asymptotically ADS. These lines in the middle, they are essentially the horizons. And the red lines are basically the past and the future singularities. And these blue slices are the large volume slices, which we just talked about at late times. And a convenient choice, which we will be looking into in our discussion, is these Hartmann-Maldacena slices. So the interior volume of these say a Hartmann-Maldacena slice grows proportional to log U0, where U0 is the Rindler time at the horizon. So the way to think about this U0 is this the point where this blue slice intersects this horizon. And this volume grows proportional to the U0. So it keeps increasing. Let's say this, as the slice evolves, the volume keeps increasing. And we create, now we'll talk about this excitations on these slices. So an interior excitation is created by acting with state-dependent operators on the right CFT. So in order to create the interior excitations, there was this proposal by Suvrat and Kyriakos in a set of papers that you can create these interior excitations by looking at this the action of state-dependent operators on the spacetime, on the black hole state. So here, this UT is an unitary operator which acts on the right CFT, and HR is the right CFT's Hamiltonian. So what this UT does, this particular UT, it controls the position of these excitations on the slice. So we can now create some other excitation in the interior, which is separated by some factors e to the power plus minus IHRT. And what these factors do is that they spatially separate the second excitation from the first one in the interior. The way to understand this is by thinking that the exterior time-like coordinate, that is this t, becomes space-like in the interior. Now, these excitations on this slice can be placed far apart from each other if t is large enough, and we can generate m number of such excitations similarly. So the picture is something like this. We have this slice, and we have generated these excitations on this slice, but they are separated far apart from each other by modulating this parameter t, which we just talked about. So in our construction, we will generate excitations with small back reaction. So for k excitations, we ensure that the number density of the excitations, which is k divided by the volume of the slice, is finitely small in the thermodynamic limit. This allows us to calculate the entropy of excitations by treating the system as a dilute gas of excitations living on the slice. And the expression of the entropy is simple to calculate. It involves it's a standard statistical mechanical calculation. So we use this Stirling approximation and other things, and we get this entropy which is proportional to the volume. So earlier we had argued that this volume increases with time. And now we have a situation where the entropy goes as volume. So the entropy of these excitations on this slice can potentially increase with time. And this is in contradiction to, so this entropy basically has this linear volume dependence, and that's why it has this dependence on time. So this leads to paradox, since we have already stated that this entropy go as area, but now it's increasing with time and it goes at volume. So this is how the paradox. Okay, so the proposed resolution is that we have not done the counting correctly. And basically in our counting, we have missed small inner products between. So semi-classical bulk states placed far apart from each other in the interior are seemingly orthogonal. However, these states have small inner products between them, which deviates from the semi-classical expectation of zero inner products. And we argue that the paradox essentially arises by neglecting such small inner products, which leads to a huge overcounting of the bulk Hilbert space. And such a huge overcounting is surprising and essentially arises due to the large dimensionality of the bulk Hilbert space, as we will illustrate later on. So let me just briefly motivate why this resolution, let me just briefly motivate why we considered this resolution. So in linearized gravity, one can calculate the inner product between two gravitational coherent states. And this inner product as expected, this inner product exponentially decays as a function of phase space distance between the corresponding classical configurations. But this description is misleading when the phase space distance is very large. So when the distance is very large, we expect that the inner product between these states go to zero. However, the inner products do not actually go to zero, but develop what is called a saturated fat tail. So they do not go to zero, but they get saturated at a particular value. And this is the motivation for overcounting and overcounting of this bulk excitations. And this consequently explains why the excitations are not really independent, leading to the paradox. So let us do a small rough counting. So the question is, how many bulk excitations can we fit using a smaller Hilbert space? So this is a problem. In a Hilbert space H of dimension n, what is the maximum number m of vectors vi which satisfy the following relation? That is, they are normalized and they have a small inner product between them. So the so the physical motivation which goes in here is that epsilon is greater than square root n. And the way to solve this problem is by considering unit vectors in the Hilbert space which live on the surface of this 2n minus 1 dimensional real sphere. So this is the one constraint. There will be this 2n dimensional real sphere, but this is the constraint. So it's a 2n minus 1 dimensional real sphere. And we can estimate the maximum number of vectors which can be embedded in this Hilbert space by dividing the surface area of this 2n minus 1 dimensional real sphere with the area of the exclusion zone. So let me just define what is exclusion zone. The exclusion zone is basically is given basically by the fact that if you take two vectors very close to each other, then this inner product might get greater than epsilon. So that defines an exclusion zone that two vectors cannot come very close to each other. And this exclusion, and we essentially divide the surface using this area of this exclusion zone. And using this, the maximum possible number of the maximum possible vectors for some small epsilon, which is like greater than 1 by square root n, it is a very large number. So m is something like n into e to the power n epsilon square by 2. And one can see that this is actually a very large number. For example, if you take n is equal to e to the power s and epsilon is e to the power minus s by 4, so that it satisfies this relation, then you can fit in a lot of vectors in such Hilbert space. So I'll not go much into detail into the checks which we looked at, but we also showed that there is no paradox in the CFT using the mentioned form of interior excitations. We also posed the paradox for single-sided pure state black holes and demonstrated why there are small inner products between candidate interior excitations there as well. And such excitations lead to qualitative and quantitative differences in spectral observables like level spacing distribution and the spectral form factor. And we qualitatively argued that this can be resolved if we think about this, if we take this overcounting into account. And within toy small n matrix models, we demonstrated how candidate interior excitations can lead to an overcounted Hilbert space. So yeah, so thank you for your time. Yeah.
Thanks, Joydeep. You can take a couple of questions.
Hi, can I ask a question?
Yeah.
This fat tail in the inner product, it's qualitatively similar to how people think of correlators having a ramp kind of thing, is it?
Yes, they are related basically. So one can see that these two things.
But to see the ramp and so on, don't you have to really know the distribution of the spectrum and so on?
Sure. So yeah.
And then you seem to be saying like we can see the fat tail just from some gravitational coherent state analysis.
So the statement is that if you take two states which are separated far apart from each other, then they would have a small inner product. So that's the statement here. So if you take two states which are separated far apart from each other, you seemingly think in effective field theory, you would think that these will have zero overlap, but they have small overlap. So that's the ingredient which is going in. And yeah, that is how this spectral form factor and the other things are also.
But I'm trying to understand this. To see the spectral form factor, so see the ramp in spectral form factor or ramp in a correlator separated in time, you have to, I thought, kind of know what is the need to know something subtle about the spectrum, like the level distribution or something. But to kind of have the same thing here, now inside the horizon, the separation time is like the spatial separation, and to see that coherent states have some fat tail in their overlaps, you don't need to know the spectral distribution and so on.
You can calculate the spectral form factor using all these excitations.
Just from some classical gravity coherent states and so on. Is that what you're saying? Or?
Not from this classical gravity, but yeah, you can actually take all these excitations into account and calculate the partition function, and then you can look at the spectral form factor.
Okay, thanks.
Okay, so why have you choose this epsilon to be greater than 1 by square root of n?
Yeah, so there is a physical motivation behind that. So like, so this is what was shown in this papers basically. So yeah, this is what was shown in these papers, that epsilon is greater than 1 by square root n. So they did some analysis and showed that it's a surprising property, and it's in a certain sense from the bulk side. So in the ADS-CFT duality, from the bulk side, you would expect that this thing that the inner products die off, but from the CFT side, you can see that this actually is a bit saturated. It develops a saturated fat tail, and it's of epsilon greater than 1 by square root n. It's quite surprising.
Thanks. Any more questions? Thank you, Joydeep.